in new and interesting areas, which I think is a very healthy part of this community. So I'm excited to be here, and thanks a lot for giving me the opportunity to speak. So I think the title is the longest and most complicated part of my talk today. I actually have a very simple, we've heard a lot of very fascinating and sophisticated things in the last couple of days, particularly some interesting mathematical perspectives that help us understand how to think about things. What I'm going to talk about today is really a very simple story related to trying to understand better the swampland of theories that look consistent, but which we don't have an F-theory realization for in 6 dimensions. And I'm going to focus on the case where we have a single U1 gauge group, which is a case that actually hasn't really been studied so much from this perspective. This is mostly based on a paper with my student Andrew Turner, which hopefully will appear, if not by the end of this week, at the beginning of next week, should appear. And also it will tie into some aspects of another recent paper by another student, Nikhil Raghuram, who will be at Virginia Tech in the fall. So, again, the idea is there's this overall program of trying to understand the set of theories that we can get from string theory, or in the case of 6D n equals 1, it seems like F theory, as we understand it so far, gives us pretty much all the theories that string theory has available in n equals 1 6D. So we have the set of F theory vacua. And then there's this larger red set of theories that we do not know any inconsistency for. These are theories that satisfy gravitational, mixed gauge gravitational anomalies, any other quantum consistency condition that we know of, which includes things like the self-duality of the charge lattice in 6D n equals 1. And the swampland, as Krumrin dubbed it years ago, is basically this red space in between the boundary of the set of theories which are acceptable and the theories we can realize from F theory. So the idea of this program, as was very nicely described by Iñaki yesterday in the context of 10 dimensions and their work now on 9 and 8 dimensions, where they're beginning to get a good handle on this. The idea is to systematically look for models that live in this in-between space, the swampland, the things that are consistent but not realized in F theory, and ask, is this something for which we realize a new string construction? If it is, then really we are defining a bigger set V star that explains this set. Is this theory actually secretly inconsistent, which would reveal a new low energy inconsistency, which would shrink the set G to a set G star? And if we can do that for all the theories in the intermediate range, then we show that, in fact, every consistent theory of quantum gravity with, say, supersymmetry in a certain dimension is realized by F theory or another string theory. Then we've shown string universality. And as Iñaki summarized yesterday, in 10 dimensions, we do know that, at least at the level of massless spectra. And they've made some nice progress in 9 and 8 dimensions. In 6 dimensions, there are some parts of the theory where we see a pretty close match, and there are other places where there's still a gap, a swampland of theories that we don't know how to deal with. And that's really what today's talk deals with. So, again, I'm going to focus on theories with a single U1 factor and charged matter, where the charges can be various integers, Q1, Q2, etc. So before we launch into the discussion of anomaly constraints on U1 theories and what we might get through F theory, let me just remind you of what we know about non-abelian gauge groups. And there the story is in some ways fairly well under control. We know that if the number of tensor multiplets is less than 9, then there's a finite number of gauge groups and massless matter spectra that are consistent with the anomaly conditions and the bright activity conditions on some of the curvature squared terms, on the F squared terms, for instance. And a good fraction of those come from F theory. So a good fraction of the models that look acceptable, in fact, we have UV realizations for. Things are under relatively good control. There are some issues with exotic matter fields, and last year, in the last year's version of this meeting in Trieste, I talked about some work that appeared in a paper with Dennis Clevers, Dave Morrison, and Nikhil Raghuram, where we explored exotic matter using a non-UFD type construction, where the divisors that carry the gauge group have singularities or non-UFD structures that enable exotic matter constructions. So we have a pretty good handle on a lot of aspects of the swampland for non-abelian gauge groups, at least for small values of the number of tensor field. So what I want to do today is really some very elementary stuff, looking at what the anomaly constraints tell us about U1 charges. And we'll see that actually the story is much less under control than this nice story of non-abelian gauge groups. So first, let me just write down the U1 anomaly conditions. And again, really very simple math today. I think the most complicated equation I'm going to write down is a Diophantine quartic equation. So no categories, no exotic singularities. There will be exotic singularities hidden under the hood, actually. This is in some ways related to Andres' talk this morning and the talk you'll hear later from Roberto. But that's sort of a structure which may underlie some of the F-theory constructions related to these solutions. But for the moment, let me just focus on the anomaly equation. So as in the non-abelian gauge group case, the anomaly coefficients, the Green-Schwarz terms, are controlled by two vectors A, and for a gauge group U1, there's a B tilde, which are vectors in this 1, t self-dual lattice that is the lattice describing dionic string charges in the low-energy theory. The couplings, the BRR and BFF couplings, are multiplied by this A and B tilde, and in the language of F theory, for instance, A is interpreted as the canonical class of the space, and the lattice, just the H2Z lattice of the base of the elliptic vibration for the F theory compactification. So in terms of A and B tilde, the U1 anomaly equations are very simple. We have a set of charges, Q1, Q2, etc., and minus A dot B tilde, again, taking the inner product in this signature 1, t lattice. That's just a number, and that number is 1/6 of the sum of the Q's, and B tilde dot B tilde is 1/3 the sum of the fourth powers of the Q's. So those are the anomaly equations, and so really my talk is about solutions to these simple Diophantine equations. And just to even simplify the story a little bit further, I'm going to look at models where there's only where there's no tensor multiples. So in F theory, this would correspond to compactifications on the base 2. And here the Diophantine equation, the left-hand side, A becomes an integer, minus A is just 3, B tilde is also an integer, so we have an integer B tilde, and the problem is to find an integer B tilde and sets of Q's that satisfy those equations. There is, of course, also the gravitational anomaly condition, H minus V is 273 minus 29T, but in this case T is 0. So you have to remember the gravitational bound as well, although as we'll see in cases that comes out automatically. Okay, so those are the anomaly equations. Let me just run over a very simple case, which is if we take t equals 0 and we restrict to charges 1 and 2. So now I'm just taking some number of charges 1, some number of charges 2. We get a couple of linear equations giving us the numbers of multiples with charge minus 1, the numbers of multiples with charge minus 2, and we can solve in terms of B tilde. And so the spectra of the allowed models in this case is simply this spectra. We have B tilde times 24 minus B tilde charge 1s, and 1/4 B tilde times B tilde minus 6 charge 2s. And of course, these numbers have to be non-negative to get a decent spectrum, so B tilde goes between 6 and 24. And the t equals 0 anomaly equations also enforce the condition that B tilde is an even integer, because otherwise this is not an integer, and we definitely want an integer number of fields with charge 2. Let me just briefly put in a slight caveat here. Sorry, the caveat comes in a moment. Okay, so those are the U1 models that satisfy the anomaly cancellation conditions in this very simple case. We can compare this with the set of SU2 models, which we also know, and we can determine, for example, by solving the anomaly equations, where we restrict only to having fundamentals and at least one adjoint. We're going to want to Higgs it down to one model. So we have SU2 models with some number of fundamentals and some non-zero number of adjoints. We solve the anomaly equations, and again, we get a similar formula. There we have 2b times 12 minus b fundamentals, and 1/2 b minus 1 times b minus 2 adjoints. So those are the which are determined simply by anomaly cancellation. There are 10 models in each of these categories, and there's a one-to-one matching between them. Because I've restricted to having at least one adjoint for SU2, we can Higgs on the adjoint, we can break the SU2 down to U1, and so each of these SU2 models can be broken to one of these U1 models. In fact, each of these SU2 models can be realized by the most straightforward F-theory construction. We use the Tate or UFD construction, where we simply tune F and G to successive orders, or we use the Tate form for SU2, which is very simple, and it gives us a construction on a degree B curve on P2. All of these U1 models come from the Morrison-Park construction, which is the simplest known way of writing down a Weierstrass model with a single U1, and there's a one-to-one match in these. So in this particular simple case, there's no swampland. We have a complete match in the set of F-theory models and the set of models that satisfy the anomaly conditions when we have no tensors and only charges 1 and 2. Let me add one small caveat related to a comment I made in Andres' talk this morning in an answer to a question of Jonathan's, where I said something slightly misleading. The philosophy of my answer, I believe, was correct, but as Ling pointed out to me, actually there's one model here where B is 24, where we only have charges 2. This is a distinct Weierstrass model from the model where we only have charges 1. So there's a model where we have 108 charge 1s and no charges 2, and there's a model with 108 charge 2 and no charges 1. Those are distinct models in F-theory because they have a different relationship, they have a different value of B tilde on the anomaly lattice. We can un-Higgs them to two different models in terms of SU2. One of them has 54 fundamentals and 1 adjoint, and one of them has 55 adjoints. However, the one with 55 adjoints actually, because of, I think this might have been in a paper by Timo and Dave, it's actually got a torsion, so there's a Z2. So it's really an SO3 model. So even though these are labeled here as charge 2s, in some sense, these are really the fundamental charge there. So in that model, you actually don't have massive charge 1s. That was the thing I said this morning that may have been misleading. There are other models that don't have charge 1s, like there are models I'll come to in a minute which have charge 2 and charge 3 massless fields and no charge 1s. And for those, we would expect massive charge 1s. So we don't need to have massless charge 1s, but this particular model actually, this with B tilde equals 24, that's the unit. Okay. So that's a very simple story. We have a complete match. If we continued on for higher T and higher Q, we would say there was no swampland and we would be happy and done. What happens at the next stage? Let's go on to higher Q. Can we match F-theory to the anomaly solutions for higher Q? Well, the answer is no, and the answer pretty badly diverges from yes, in the sense that already when we go to 3 distinct charges, which could be arbitrary, we find an infinite family of solutions to the anomaly equations. If we take 54 charge Q, 54 charge R, and 54 charge Q plus R fields, those satisfy the anomaly equations with this value of B tilde, and there is no constraint I am aware of that rules out those theories from the low energy point of view. So we have an infinite set of apparently anomaly consistent models with no real problem. I should note that for non-abelian gauge groups in matter, you don't have this sort of problem because the representations get bigger and bigger as the representations get more complicated. So you rapidly violate the gravitational anomaly bound. Here, we've only got 162 fields, no matter what P, Q, and R are. And you can continue, and it gets worse. If you have 4 different charges, here's a set of 4 charges, 54 of each of them, where A, B, C, D satisfy these simple expressions in terms of 2 non-negative integers, m and n, and we get another infinite family. Okay, so this is perhaps not surprising from the simple Diophantine equations that I wrote down. The Diophantine equations basically say B tilde is proportional to the sum of the Q squareds, B tilde squared is proportional to the sum of the Q to the 4th. So we can think of this roughly in Q space as an intersection between a sphere, something which satisfies sum of the Q squareds equals a constant, with a quartic surface of the same dimensionality. And so you just use a simple scaling argument, and as B tilde gets larger, the number of solutions should go as B tilde to the m minus 4 over 2 if we have m distinct charges. So we have expanded infinite families, and the asymptotics of the equations suggest that these infinite families will just get bigger and bigger as the number of distinct charges goes up. So we have a very badly divergent number of solutions of the anomaly equations. But we also know that there are a finite number of models, finite number of distinct spectra that can come from F-theory. This follows, on the one hand, from the proof of Gross that the number of elliptic Calabi-Yau threefolds is finite up to birational equivalence, and there's a slightly more constructive or slightly more direct that we had in an old with Vijay Kumar and Dave Morrison, where we use the Hilbert basis theorem to show that basically if you use Antonella Grassi's result that everything is a Weierstrass over a blow-up of one of the Hirzebruchs or P2, that everything lives in some stratum of the set of Weierstrass models over a finite set of minimal models, and there's a finite set of combinations, finite set of algebraically closed sets that you can form in that way. So for numerous reasons, we know that F-theory gives us a finite number of spectra, and yet there are an infinite number of anomaly-free spectra with a single U1. Also, this is somewhat different from our experience with non-abelian gauge groups, where there's a finite spectrum, at least at values of t. Okay, so we have an infinite swampland, and so that's one part of the that's one big part of the punchline of the talk. Let me explore in the remainder of the talk a little bit more what we can say about this infinite swampland. Okay, so let's look at some examples. Let's now move on to things with charges 1, 2, and 3 at t equals 0. Again, sort of the next simplest case. So we can solve those anomaly equations. It's just some Diophantine equations in integers. Turns out there are 245 solutions. And we can ask, okay, which ones of these we know how to realize in a really well understood way from F-theory? So one useful thing to do, just as we did for the charge 1 and 2 case, is to look at which ones we can un-Higgs to, say, an SU2 or SU3 model, because those are the ones that we could then more easily realize in F-theory. As we all, I think, appreciate, it's much easier to design or engineer a non-abelian gauge group in F-theory than it is to engineer an abelian gauge group. We're learning a lot about abelian gauge groups. So which of these 245 come from F-theory? Well, many of them are un-Higgsable to an SU2 with triple symmetric matter. So as soon as you go to triple symmetric matter, that's an exotic matter configuration. It implies that the divisor supporting the SU2 has to be singular, and you need to go to this non-UFD construction that we developed with Dave, Dennis, and Nikhil that I talked about last year. Some of these models can be realized in that sort of construction. We do not have a comprehensive understanding of what situations you can implement that construction in, so we don't have a complete set of which one of those 199 come from an SU2 that is in fact a non-UFD realization. Some of them are un-Higgsable to SU3 with just adjoints and fundamentals, and then you can Higgs on 2 adjoints. So those that we know come from F-theory. So there are some we can say these definitely come from F-theory. And there are a few others that can be realized by a non-UFD construction, a non-UFD based U1 construction with charge 3. Some examples of this were found in this paper by Dennis, Paul, and others, Paragua, and Reuter, when they looked at different fibers for elliptic fibrations, and this was combined with this non-UFD construction by Nikhil Raghuram last year, and he wrote down a fairly general construction, a systematic way of doing a non-UFD. It's not a Morrison-Park. Morrison really only covers charges 1 and 2, so this is a non-UFD generalized U1 construction that includes charges 3. So some of them are realized in that way, but not all. So of these 245 spectra, more than half are realized in F-theory in some way we understand, but the other ones, we don't even know which ones are realizable in F-theory and which ones aren't. There are none of them that we can definitely rule out, because we don't really understand either the most general SU2 or the most general non-UFD Q equals 3 construction. We can move on to Q equals 4, and the situation just gets worse. There's an even larger number of models. Again, Nikhil Raghuram wrote down an explicit realization of a small class of U1 models with charge 4, but we don't have a general understanding of that. We know that you can get charges Q equals 5 and Q equals 6 because you can construct non-abelian models with SU5 or SU6 tuned on a quartic on 2, and then Higgs. So the quartic gives you 3 adjoints. You can Higgs on 2 of the adjoints, and that gives you a charge 5 or charge 6. Higgsing is not known. We don't know the Weierstrass model that you get to after that Higgsing. So the biggest thing that we can get in any known construction using Higgsing in F-theory is charge Q equals 6. It's very hard, it seems, to go beyond that with this kind of construction. Roberto may or may not choose to comment in the talk later this afternoon on what the technology that he and Andres and Dave and Fatsi have been developing might have to say about this. I'll leave it to him to choose what to say about that, but I think there's some hints there that may relate to what I'm saying here. But anyway, the biggest we know we can get is Q equals 6. We don't know we can get anything bigger. There's an infinite set of apparently consistent models. And even though there's an infinite set of apparently inconsistent models and a finite set of them come from F-theory, there is not a single model in that infinite set that we can point at and say, this one cannot come from F-theory. So it shows that we have a real lack of understanding, in my mind, both of the low energy constraints and of F-theory. Okay. So we have this big swamp. Let me point at an interesting relation that may give some hints, but I'm not sure what it tells us exactly. If we look at UFD constructions of SUN models or Morrison, for instance, the UFD construction of SU2 model proceeds by writing F as a power series, G as a power series, and the leading term in F is phi squared, leading term in G is phi cubed, so that they automatically cancel at leading order in sigma. If you look at this construction, F1 is in the class minus 4a minus b. And if F1 vanishes, then everything vanishes. The discriminant is identically 0, and you'd have a bad model. So for these models, B is less than or equal to minus 4a in the positivity cone in the string charge lattice. The anomaly constraint is B dot B is less than or equal to minus 4a dot B. These are strikingly similar equations. This looks like a projection of this stronger equation. Similarly, the Morrison model needs to have B tilde less than or equal to minus 8a, and the anomaly constraint is B tilde is less than or equal to minus 8a dot to B tilde, assuming charges Q equals 1 and 2. So for a little while, we thought, wow, we found these stronger constraints. These must be the real low energy constraints. That must solve our problem. At least we should be able to try to prove those constraints for low energy. Looks very compelling. Are they actual constraints? The problem is they're not. These non-UFD constructions, it turns out, can give U1 and SU2 models that violate those stronger bounds. So this is pretty mysterious. So there's some examples of that with Nikhil and Andrew and Yinan Wang, who some of these things we're working on understanding those better. The only really clear bound we know of from F-theory is the so-called Kodaira bound, which says that, just from the fact that the discriminant is minus 12a, n times b is less than or equal to that, which follows just from the fact that the discriminant has diminished order n, which is minus 12. There are examples of U1s with charges that violate, that unhigs to an SU2 that violate that bound. So these are definitely in the swampland. For instance, there's an SU2 model with 76 adjoints and no fundamentals. That is definitely in the swamp. If you Higgs it, you get a model with 150 U1 charge 2s, but we don't know that this can't be realized in some more exotic way from F-theory. So we don't even have an analog of the Kodaira constraint for U1 models. There are further constraints I'll just mention briefly because I'm running out of time. There's a constraint from F-theory, it seems, that B tilde must be even. This comes either from Morrison-Park or Higgsing SUN model. It's not quite clear in the low energy theory, but basically this comes from the quantization of U1 instantons. And there was a recently by Monnier, Moore, and Park, where with the mild assumption, which is that the theory can be compactified on an arbitrary manifold and you can put it in an arbitrary bundle and you don't have, then Iñaki mentioned some analogous assumptions, but then pointed out that you could have some logical that rules out certain sectors. With the mild assumption that that sort of thing doesn't happen, they proved that B tilde is even. So it looks like that constraint that comes from F-theory looks like it's also a low energy constraint. There are also subtle issues about the positivity cone. In T equals 1, for instance, there are two unimodular lattices. They can have different cones. From F-theory, there are certain cones of positivity that can arise. We don't really know what the low energy constraints are on the positivity. There are various choices of the A vector. From F-theory, we get 2, 2 on the even lattice. There's also the possibility of 4, 1, but that doesn't seem to arise from F-theory. So that's another thing that we should be able to rule out from some low energy constraint, or else it'll be swampland. So there's a big question, which is how much of the positivity cone can we understand from the low energy theory? It's a question I've been bothering people about for years now, which is if you have a -3 curve, why do you have to have an SU3 from the point of view of the low energy theory? Okay, I'm out of time. Let me just summarize. I'm just going to make, basically this talk is presenting you with a list of challenges and questions. What combinations of U1 charges can arise in F theory? We don't know. What is the maximum Q? Maybe it's 6. Can we prove it? We might hear something about that later this afternoon. Is there a physical significance in low energy theory for these UFD or Morrison-Park models which give these inequalities that closely mirror the anomaly bounds? Can we prove the Kodaira bound from low energy? This would give a constraint on the relationship in higher derivative terms, R squared terms, and F squared terms. Can we find low energy conditions that limit the set of possible charges and cut down this infinite swampland? And then we could extend this further to talk about U1s in the presence of UNs, and many of you here, Craig, Sakura Wong, Miriam Ling, others have thought about these questions. I think these are all great questions. I'll leave them for you and stop.
The non-UFD construction for smooth curves.
Yes.
So usually you adjoin roots which are not in the ring initially, right? If I understand the non-UFD construction
So
correctly.
the way when we wrote the non-UFD paper, we were looking for these higher genus representations which have to live at singularities in the curve. It turns out, actually, that you can have a non-UFD construction anytime the genus is greater than 0, even if it is smooth. So, for example, you can have a non-UFD construction of an SU2 model on a smooth genus 4 curve.
But the ring is UFD, no?
What's that? The ring is not UFD. No, actually, the global ring, it took me a while to understand this. The global ring on a genus 1 curve, there's a local ring around any which is a UFD, but if you really make a global ring, we have explicit constructions on a genus 1 curve, on a higher genus curve of an F and a G, which give you an SU2, and they are not exact squares and cubes. And it's on a smooth. I didn't appreciate for a while this could happen, but it can. So there's non-UFD constructions, even of models with charge 1 and 2 and no higher charges. For U1s, and there are non-UFD constructions of an SU2 that only have fundamentals and adjoints, and they violate this this condition we were trying to push on, which is closely to the anomaly condition. Possible there's something wrong with that. I invite you to find an error, but I think that's the correct statement.
So this probably is unrelated to the U1s that you're talking about, but I think you wrote a paper about why in 10-dimension 498 rank group does not mean use U1 to the 498 or something, and the argument was based on the string, if I remember.
Yeah, so basically it was kind of a simple thing that I think I missed this, but basically if you try to make things compatible with supersymmetry, excuse me, at the same time as gauge invariance, you're forced to have a trivial kinetic term for the gauge group. Basically you're forced to a limit of trivial gauge coupling. That does not happen for these models.
So you have checked those statements?
Yeah. The fact that B tilde is non-zero, it's a non-zero integer, immediately says there's not a problem there. Because B tilde is also the thing that appears in the gauge kinetic term. Yeah. There were some models that John Schwartz had written down where he thought there was an infinite family of 6D models that satisfied anomaly cancellation, and those violated that kind of constraint.
Ah, I see.
But these models all are fine from that respect.
And then the other one is that, are there global high form symmetries in these theories if you just study the gauge group to be this U1 with certain charge? In other words, does the choice of charge give you extra global symmetries? Higher form symmetries, maybe?
That's a great question. I'm not aware of that happening, but it would be interesting if there's some further structure like that. Iñaki?
Could you elaborate on that thing you said, the constraints on relationship between F squared and R squared terms?
It's just that A is the coefficient of capital B wedge R, and B is the coefficient of capital B wedge F, the Green-Schwartz anomaly terms. Those are related by supersymmetry to the F squared term and the R squared term. So, for example, the fact that minus A is an effective divisor. So I'm start with B. The fact that B for a non-abelian gauge group effective divisor tells you that the coefficient of F squared has the proper sign to be a good gauge kinetic term. It's got a negative sign. And so that's something we understand from low energy. the fact that minus A is positive, is in the positive cone, tells you that everywhere in Kähler moduli space, the R squared term has a certain sign. And signs on the R squared, there was a paper by Chung and Remen a year or two ago where they proved a way that's relevant to these 6D theories that the sign on the R squared term is constrained. Now, the Kodaira condition relates B and A. So it relates the coefficient of the R squared term to the coefficient of the F squared term. So it says that not only is negative A positive, but negative A is bigger than a certain lower bound. And so therefore putting a lower bound on the magnitude of the R squared term. So somehow any model consistent with F theory that has, say, an SUN gauge group will have an R squared term whose coefficient is lower bounded by the F squared term. And we don't understand how to see that from the low energy theories. That's what that is all about. Can we find from the low energy theory a reason why not only, as Chung and Remen showed, the R squared term has a certain sign, but the magnitude is bigger than a certain value?
Thanks.
Yeah.
Good workout. You probably said it, but I missed it. So in the Diophantine equations you wrote down, where was the condition that the massive states are populating the rest of the charge lattice?
Good. So it's not built in. I think it's just a true fact. So let me give you an example. I mean, there are two examples that are relevant. One is the one I tried to use this morning in answer to your question, which was actually, as Ling pointed out to me, it was not a good example of that in the sense that I gave this example of a theory, a U1 theory that just has charge 2 where B tilde is 24. Okay, in that case, really, that 2 is the unit charge because when we un-Higgs to the SU2, this is really an SO3. There's nothing with a charge that's odd, and therefore this is an example where we don't need to find a massive state of charge 1 because this is the unit charge. There's another example, though, that I sort of went past quickly, which is relevant, which is if you look at charges 1, 2, and 3, there are some models that just have charge 2 and charge 3. Massless. They just have massless charge 2 and charge 3. We haven't anywhere put in the condition that you have to have a massive charge 1. The conjecture about having to have all possible charges, which I think there may be an upcoming paper by that may in the ADS CFT context by Harlow and Oguri, but that conjecture would suggest that in those models there has to be a massive charge 1 state, but that's actually kind of trivial in the following sense. There you have a charge 2 and a charge 3. So if I take a charge 3 and a charge minus 2 and I put them together, I'll have some object in the Hilbert space that transforms as a charge 1 object. So there are quantum states of the theory that have charge 1.
Yeah, but that's assuming that you have like a charge n and charge n minus 1. So in the Diophantine equations you wrote down, is it clear that...
So if the conjecture is true, it would mean we should not be able to find any models which don't have massive states, at least, of charge 1 if they don't have massless states of charge 1. And I gave you a couple of examples of places where that conjecture is satisfied. I don't know of any examples where it's not satisfied, but it's not an input.
No, but all the infinite families satisfy this?
Not all the infinite families satisfy. Well, we don't know. There are elements of those infinite families that don't satisfy them, so those probably are inconsistent. Well, we don't know whether they satisfy them because we don't know. There's a little bit of subtlety, which is that the...
My question is whether the infinite families may be removed by imposing
No, you can't remove the infinite families. They're definitely, if I take P and Q relatively prime, for every pair of relatively prime integers, P and Q, there's a model which has 54 P's, 54 Q's, 54 P plus Q's, and must have massive states of charge 1. P and Q are relatively prime, and by some high school theorem, there's a linear combination of those which gives you 1, right? And therefore, there's some state in the Hilbert space that is of charge 1. So there are infinite families that must have massive states of charge 1. So we can't rule out the infinite families based on that. Yeah, good question. Other questions?